All right, so now let's go use some Maclaurin series in some integrals. Some a little more challenging Maclaurin series. Okay, so this has x subtract sine of x. So we haven't done that before, so let's try it. So let's start off with what sine of x is. So you know the Maclaurin series for sine of x is this. It starts at 0 and goes to infinity. So just because I want to look at the first term here, what happens when I plug in n equals 0? So if I plug in n equals 0 into here, I get negative 1 to the 0, so that's positive, x to the 1 power, and then over 1. And then when I plug in n equal 1, I'll get minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then, whoops, and then it keeps going on, right? And it changes sign, so the next term would be negative. Okay, so these are the first few terms of sine of x. Look at what this is saying. It's saying make the function x minus this. So I'm making the function x, equal x minus sine of x. So I'm just going to write in the first few terms. Okay, and I know the pattern of how it goes. So x subtract x, that's gone. If I take this negative sign and distribute it through, I would get a positive x cubed over 3 factorial. And then a negative x to the 5th over 5 factorial. And then a positive, okay. So dot, 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 dot. Okay, so I want to write this as a Maclaurin sum. Okay, so let's think about this. I don't have to start at 0, correct? How about I start at 1? So if I start at 1, I want to generate these terms that are going with this pattern. So how about if I start with the x? Won't it be 2n plus 1? Because if I plug in 1, I get to the 3rd power. If I plug in 2, I get to the 5th power. So that will work. How about if I put in 2n plus 1 factorial on the denominator? That will work. So what is it I have to do here for the alternating sign? Does negative 1 to the n work? If I put in n equal 1, that makes it negative. That does not work. So let's change it to plus 1. Now I've got a positive term for the first term, a negative term for the second term. There it is. All right. So this one here is saying the same thing. It has x minus sine of x, and then it divides it by x. So let's take this. N equal 1. And divide it by x squared, which means put that down here. So let's simplify our x's. So join those together. It's a negative, there we go. Okay. 2n plus 1 factorial. Put this up here, so I get 2n plus 1 minus 2 for the exponent, right? So 2n minus 1. All right, so I did that one in 2 parts for you. So now let's go through this one in all one fell swoop. So I'm going to always encourage you to go slow and start off with what you know for e, for the, just the one function. Do one step at a time. So what is e to the 3x? That'll be 3x to the n over n factorial. So let's separate that. Okay. Now let's plug in or subtract off 1. So let's plug in the first few terms. So when I plug in n equals 0, 3 to the 0 is 1, x to the 0 is 1. So the first term is 1. Then I plug in n equal 1. So I get 3x over 1 plus 3 squared, x squared, 2 factorial, dot, 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 dot. Okay, so if I want to take e to the 3x minus 1, and I'm just going to write down the first few terms, dot, 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 right? Subtract 1. What that turns into is I'm just taking off the first term. So I'm starting with this, 3x, 3x squared over 2 factorial, dot, dot, dot. Okay, so if I wanted to write this one as a sum, I could start this sum at 1. So 3 to the n, x to the n factorial. Then let's finish off by dividing through by x squared. So e to the 3x minus 1 divided by x squared, x to the n factorial, and then put this x squared in the denominator. So 3 to the n factorial. So let's join these x's together. So that would be x to the n minus 2. Okay, so going one step further, finishing up with this example. So let's find the Maclaurin series for this, and then we'll integrate it. All right, so e to the x squared will be x squared to the n over n factorial. So that's x to the 2n over n factorial. Okay, now let's multiply that by x squared. Okay, so I'm going to add these exponents. All right, so now I want to take this and put it in the integral. So I want to say integral, of this. And if you look at this, you can see that this is an impossible integral. So this is a good thing. All right, that I can do the integral this way. So I carry along the 1 over n factorial, because that's the n's that don't get integrated. It's just the x that I add 1 to the exponent of, right? So I'll get x to the 2n plus 3 over 2n plus 3 plus c.